Okay, so to start off, I just want to talk about sets in general because when we talk about linear inequalities and we give our solutions, we need to kind of understand sets and subsets and just the different types of numbers we have, especially because a lot of answers we write as like is a real number, and so you need to know what that means. So if we just, I'm just going to start from the very beginning. The numbers we count with, when we start counting, we always start counting with 1. So the set of numbers we count with, and sets are always written with a curly brace. So I think it's just technically called a brace, but I usually call it a curly brace so that people don't get confused with the other types of symbols. But that is our set notation. Anything inside those symbols is indicating that we have a set. And so the counting numbers is called the natural numbers. And we call them the natural numbers because that is what we naturally do when we start counting. That's just how they got their name. And they do have a special symbol. That's how I write it by hand. If you look in the textbook, it's written a little bit differently, but it's basically kind of uses double bars to indicate it. So that's just an N for natural numbers. Now, historically, people they started counting with 1. 0 did not actually exist for quite a while. And so when we start adding in 0 and an understanding of what 0 is, that's where we start getting whole numbers. So when you add in 0 and you start counting from 0, that gives us the set of whole numbers. And our text uses like a W symbol for it. That is, I have not seen that symbol very often because we don't usually talk about just whole numbers. And you may often refer to negatives as negative whole numbers, or just say whole numbers include negatives, but technically once you start including negative numbers, those have a different name, which are called integers. And this is sort of the order that they came about historically as well, that 0 was before negatives. So these dots that I'm writing in just show that things are going on forever, and it's just following a pattern. And so once you start including negatives, that's where we get integers. And that symbol is a Z. And that actually comes from the German word for integers. I don't know what the word is, but it starts with the letter Z. So that's why we have a Z for that symbol. So we've got our numbers we count with. We added in 0. We added in negatives. And then the next thing that you add in are fractions and decimals. So numbers that we can write as fractions and decimals are rational numbers. And so we usually, the book kind of just defines it in words, but the way we usually define it is as a fraction, P over Q. P is usually always used for the top, Q is used for the bottom. And we kind of put it in set notation. So this is going into the sort of way that you write things when you're solving inequalities. So we have a vertical bar, and that vertical bar sort of means where, or it kind of gives you like, these are the rules it's going to follow. So the rules are going to be after that vertical bar. And then P and Q, they are integers because we can have positive or negative numbers in a fraction. And we use this special symbol that's a kind of curved E, and that means is an element of, and then you would say integers, or you can use the symbol. And then this is basically rational numbers, which we have this symbol as Q. So this is really where we get into set notation. So this notation that I wrote, this is called set builder notation. And this notation is used when it's not possible to write the numbers as a pattern. Like I can't really write as I did with the whole numbers or the integers rational numbers because there are basically, I mean, there's an infinite numbers of fractions and decimals, and there's no real pattern to how you could write them. And so we use this set builder notation. So basically the first part here is our rule to write it. So it's writing as a fraction. So I'll say rule for writing. And then the vertical bar, I read that kind of as the word where. So it's P over Q, where P and Q. And then we have this symbol, our elements of, which just means they belong to the set, and then it belongs to the set Z or integers. So it's a condensed way of writing rational numbers are numbers that can be written as fractions, and that includes decimals that can be written as fractions, and even whole numbers and integers that can be written as fractions. So all integers can be written as fractions if you just write them over 1. So rational numbers basically include everything we've talked about previously. They include the integers, whole numbers, natural numbers, all that stuff. But they also include decimals and fractions. But there are some decimals that we can't write as a fraction. And so those are what we call irrational numbers, because not every decimal can be written as a fraction. And we don't really have, there's not even a way to do set builder notation for that. There's no way to write it as a set. So we've got irrational numbers, and our book uses the symbol of like a double H thing, which I've actually never seen before. And I think this is specific to our book because it says, which we will denote by H, as if it's like that's their special symbol. I guess one way that I could write this is it's a number X, where X is not an element. And so you can use the element symbol and put a slash through it. And it's not a rational number, because basically a number is rational or irrational. It can be written as a fraction or it can't be written as a fraction. So there's no overlap between those two sets. And so I could just write it in terms of, well, it's not the other thing. And irrational numbers are things like pi, because that goes on forever. Euler's number E is another example of an irrational number. And then we've got most square roots. If the square root does not come out to a whole number, then it's an irrational number and it goes on forever. So that's our irrational numbers, and that's an example, again, of set builder notation, where I'm just trying to write it in terms of things that we've written already. And then the last set of numbers we have are real numbers, and that's basically everything. Any number that we know of is a real number. And for real numbers, we use an R for real. And since that's basically what we work with in life is real numbers, whole numbers, decimals, fractions, square roots. That's what pops up a lot when you're solving. It's mostly you have real numbers when you solve. And so what we could write this is that it's just some number, we can call this X, where X is a rational number or X is an irrational number. It's basically one or the other. So that's one way that we can kind of write it as a set. So we're defining the number on the left, and then your rule is to the right of the line. And the important thing to know about all these sets of numbers is that they're subsets. So like the whole numbers contain natural numbers. Integers contain whole numbers, which then also contain natural numbers. So there's overlap between these sets. And so I could give you a number like 5. A 5 is considered a real number. It's considered a rational number because I can write it as a fraction. It's an integer. it's a whole number, and it's a natural number. So it fits into multiple groups, but these groups are basically subsets of other groups because we're adding numbers to the group to get a new name. And there's actually an image in the text. Let's see if I can get this to paste. I don't know. Sometimes images don't paste. Okay. So this actually comes from the textbook, kind of showing, it has, I don't know why that's weird right there with a black background. But it's basically showing that like natural numbers are a subset of whole numbers. We basically added in the number 0 and we have whole numbers. Then we add in the negatives and we get integers. Then we add in fractions and decimals, we get rational numbers. And then there's no overlap between the irrational numbers, so that's why it's completely separate. And then we've got real numbers that's supposed to say real numbers there. That's like everything. So we need to understand sets of numbers because that helps us understand our solutions. And later on in class, we're going to talk about complex numbers. And so real numbers are actually complex numbers, and so that fits into a bigger set of numbers. But it just gives you an idea, just an understanding, especially if you're doing like if you're programming. Usually you work with integers when you're programming, but with math, usually we're working with real numbers. And just so having an understanding of these systems kind of helps you understand what possible numbers you have as your answer and what makes sense in terms of your example, especially with real world problems. Some examples don't make sense to have real numbers. Maybe only whole numbers make sense because you can't have negatives. So things like that. So that's sets in general, and some other set notation things that we should know before we start getting into inequalities. So I talked about subsets, which is basically it's a set contained inside another set. We've got, the book talks about mutual exclusively. That's not really important, but one thing that we do have is called the empty set. And that is just literally sets, like the curly braces with nothing inside it. And that means there's nothing, no number that fits into that category, basically. So if you were solving something and you got no solution, you could write that as the empty set. So this could be something that you could write as no solution because there's no number that works. And we sometimes use a symbol of a 0 with a slash through it to indicate the empty set. So you do not want to write your zeros that way because that actually is a specific symbol meaning empty set. So I have seen some people write zeros with slashes. You don't want to do that because in math that actually is a symbol for something else. So that's another symbol. See, I mentioned that's the set builder notation. When you just list the numbers, that's called roster notation because it's like a roster is basically listing something. If you think back, probably in elementary school, there would be a list of students and they would call it a roster. I think that's the only time I actually heard that term other than math is in school. And just listing everything that's in there is just a roster. So that's why they call that roster method. But then set builders because it tells you how to create the set. So that's why we have that notation there. And then we also have what's called interval notation. So let me open the textbook so I can go to our linear inequalities, talk about sets, union, intersection, all that kind of stuff, because that's really important. When we talk about solving linear inequalities, unions and intersections are really important when we go, I think it's week 3, where we start talking about absolute value inequalities. Later on, we'll have polynomial inequalities and rational inequalities, and so those also use unions and intersections. If you have to go on a pre-calculus or calculus, you're going to be using intersections and unions. So that's a really important concept to have and to kind of understand how we write different types of notation and how we use all these symbols and everything like that. So what I like to do is sort of make a chart of our inequality symbols what that would look like if we used set builder notation, and then what it would look like if we kind of graphed it on a number line, and then what it looks like if we have interval notation. So I'm just going to make a chart. So we're going to have the inequality, and then we're going to have set builder notation. And then I actually find that graphing makes it easier to do the interval notation. So we're going to, actually I should just say graph, and then the interval notation. Let's actually put that underneath here. So I could actually start with an actual equality where you have two numbers equal to each other, and we'll just indicate those by A and B just to represent any number. So if you just have two numbers and they're the exact same number, as a set builder, we would basically just write x is equal to b, and then we would have that vertical line. And then basically, if it's only integers that are equal to each other, you would say that. You would basically list what set of number this is. But usually, we use real numbers. So I'm just using the shortcut notation here where a and b are elements of real numbers, or basically they are real numbers. That's what we're reading that as. So if you have two numbers that are equal to each other, and you put this on a number line, and on the number line we have negative infinity, and so I guess a sideways 8 is the infinity symbol, and then we have positive infinity. So infinity, basically, it's not a number that we can reach. It's just indicating going as big as you can and as small as you can. So we just have a number line here. And if we were to indicate that A is equal to B, that is equal to some number, I can just label that same point as A and B, and you'd basically just be a closed circle. And then your interval notation, here, let's actually make this a little less confusing, because a lot of people are familiar with using x to represent a number. So let's say x is equal to a, and we'll do that. And let's say the number for x is a. So your solution, this is just indicating a solution, like when you're solving for x. So when you write it in interval notation, you would just write that single number, and then it would be in a set. So actually, that's not interval. Well, I could write the set builder notation like that. Interval notation, what I could do, we don't really write interval notation for that, so I'll just leave that blank. But we basically just write it as a set, and you just have it in a curly brace just to indicate that there's a single number there. And this is this equality as opposed to inequality. And the in part just means it's not equal, so it's something else. So we usually use for our inequalities less than, greater than, less than or equal to, greater than equal to, all of those things. And so I'm going to stick with my x here so we don't get too confusing here. But let's do the less thans first. So let's say we solve something, we have x is less than a. So a is just some number, x is less than that. That is our solution. Now a could be, let's say a is equal to 2, so x is less than 2. That inequality says that we have multiple solutions and they're all numbers less than 2. So they could be the number 1 because that's less than 2. Could be 0. Could be negative 5 million. It could be negative pi. We have an infinite number of solutions, so we can't actually write down every possible answer here. But we know that they're going to be real numbers because that's what we work with in math. So it's including, it could be decimals, it could be whole numbers, it could be integers, but they're all less than this specific number. So when we write this as a set, we just take our inequality that we had, and that's in the left part because that's our rule basically. And then on the right, usually we don't bother writing x. We'll just say that a, which is the number, or we could write x there. But we're just indicating that whatever that number is, and yeah, let's just do for consistency, do x. But they're real numbers. All of our solutions are real numbers. Actually, let's keep it with x because x is the solution part. So we're just saying whatever numbers, they follow that rule, they're less than a, and they're real numbers. So that is what that set builder notation is sort of indicating there. And in Alex, what they actually want you to write, they don't use the symbol like that. You would actually write is a real number. Now when we're graphing on a number line, so I'm going to put a. I don't know if a is positive. I don't know if a is negative. I'm just going to have it on this number line here. Less than means that all of our possible solutions are left of that value because they're smaller. So you basically are covering all the lines left to that. And then that includes the arrow because it's going forever basically to the left. So when we use less than or greater than symbols, we don't use open or closed dots so much when we graph. We use parentheses and brackets, and that's because those are specific symbols used in interval notation. So for less than or greater than, for those particular symbols, we always use parentheses. So less than and greater than use our parentheses symbols. If it's less than or equal to, those use brackets. So those are brackets, they're square brackets if you want to call them that. And the way you can think about this is if it's less than, that endpoint is not included. So I think about the parentheses curving away from it. It's not touching it to indicate that it's not included. For a less than or equal to or greater than or equal to, the bracket has a hard wall that you can touch basically because it's not curved. So you can think of that as the answer, that endpoint is included because it's equal to. It can equal that part, so it has that hard cutoff there that you can touch. So that's a bracket. It's harder. And so that's how I think of the parentheses and the brackets. And so you have to decide which symbol are you using. And here for less than, we're using parentheses. And it faces the direction that you shaded. So we're going to put a parenthesis on our endpoint here, A, that cutoff. And it faces the direction that we shaded. So it's facing to the left. So when we go to interval notation is a way of writing these where you have a left endpoint and a right endpoint, and then you use parentheses and brackets. It's called interval notation because it's basically telling you the interval you are shading, the left part and the right part, kind of where you're in between. And you basically read the graph. So, and you always read the graph left to right. So we always go left to right, which is the smallest to the largest. So on the left, where I stop shading is at negative infinity. So we consider that a left endpoint. And then I shaded all the way to A, that part where we stopped because we're less than A. So I'm going to write those with a comma, so it's left endpoint, right endpoint, and then I needed to decide whether I use parentheses or brackets. So at A, on my graph, I have parenthesis, and that is the same thing that you use in interval notation. So I'm also going to have a parenthesis there. On the left, you can think of the arrow as sort of like a parenthesis. You can see that it forms the same sort of shape. And we're going to use a parenthesis there. Negative infinity or positive infinity, always use parenthesis because we can't actually touch those numbers. It's not an actual number that we can hit because it goes on forever. So we can't use a bracket because we can't actually equal that thing. So they always use parentheses. And you can kind of think of it as that arrow sort of it looks like a pointed parenthesis to kind of remind yourself that that's how you write your answer. So an example of this with numbers is if you solved something and we had x is less than -3, we would have in set builder notation x is less than -3, where x is a real number. On the graph, I always put 0 on there, and then we would have -3, and then it's a parenthesis at -3, and then we shade. And then in interval notation, this would be -infinity to -3. So that a is just representing some number, whatever you get from solving. And this is how we write it. And it doesn't matter what that number is, it's always going to be written this way. And when you're graphing these things in ALEKS, when you're asked to do the graphing part, you have to put the parenthesis or the bracket in first before you do the line shading, because ALEKS is going to want to shade the whole line if you don't do that. So you have to put in the parenthesis or bracket first, then you pick what side you're shading. So if you have something that's in between, you're going to have to put both of those in first. So similar to the less than, a is the less than or equal to. And the set builder looks almost exactly the same. It's just literally a change on that symbol here, where instead of the less than, we use less than or equal to. So those are the only things that changed, only thing that changed here. And when we graph it, the only thing that changes is that instead of a parenthesis at a, we use a bracket because it's a less than or equal to. So I would have a bracket facing the smaller numbers, the less than numbers. So that's the only difference between these two, is one has a parenthesis, one has a bracket. So when you're doing this on paper, you want to be very clear that your parentheses and brackets don't look similar, because that's the only difference when you're looking at it as a graph. And then in interval notation, we still have the parenthesis at -infinity because infinity always has parentheses. And we still have a, but now it's a bracket. So the only thing that changed in interval notation is that parenthesis to a bracket. And that was because of the symbol. It went from less than to less than or equal to. So next would be greater than. So the set builder notation looks almost exactly the same. Again, the only thing that really changes is that it's greater than now. When you have your number line, still going to have a on my number line. What changes here now is that we're greater than, which means now we're on the right side. So now I'm shading to the right. But it's a greater than symbol. I don't have that line underneath, so that's going to be parenthesis. So it's basically a flip-flop from the less than. It's now reversed image, a mirror image, and now it's greater than. And when we put this in interval notation, it also sort of looks like a mirror image. On the left, we're starting at a, and then we're going to positive infinity on the right. We have a parenthesis at A, and then infinity has a parenthesis, because infinity always has a parenthesis. And when this changes to greater than or equal to, we just have minor changes. Minor changes in our set builder notation. Minor changes in our graph, where the parenthesis turns into a bracket. And then we'll have minor changes in the interval notation. I am going to email out this document, so don't worry. You'll get a copy of this so you can have this for your notes.
Everything you're putting on the screen we'll have a copy of?
Yes.
Okay, awesome, great.
Yeah. So the only difference here between the greater than and the greater than or equal to is one minor change in our set builder notation, the minor change on the graph from the parenthesis to the bracket, and then the minor change in our interval notation there between a parenthesis or a bracket. Math is one of these things where all these little things, these little changes in symbols really makes a difference in what it means. So those are all the basic inequalities, and then we have what are called the compound inequalities, where you have two inequalities and x is in the middle. So the most simple one is if x is between two numbers a and b. And so these are compound inequalities. And this is where we start kind of getting into the union and intersection ideas, especially when you start trying to find unions and intersections. So the set builder notation is going to be very similar. It's just, we're just literally changing whatever is on the left side of that bar, the vertical bar there. The graph is what's different. So we always write compound inequalities with the smallest number on the left and the largest number on the right, so that x is between, and we go from left to right, small to big. So that means a is on the left, b is on the right. So our inequality here is indicating that x is in between these two numbers, so that's where our shading is. Our answer is in between these two endpoints. And then we're looking at our symbols. So they're both less than, which means we're not including the endpoint, so they're parentheses. And so the parenthesis faces the shading, so we end up with something that looks like that, which kind of reminds me of like a Star Wars Star Wars plane or something like that. So that's how we graph that our answer is in between A and B. And if you're going to graph that in Alex, you have to put both parentheses before you click the shading, before you click on the line to shade it in between. And this is actually almost easier to put in inequalities or interval notation, because you just literally go from A to B. And I have parentheses on both ends, so I just literally write it with parentheses. It's kind of like left to right, exactly what you're looking at. And we could have minor changes. So I can make one of the symbols a less than or equal to and the other one not. And set builder notation would look almost exactly the same. On our graph, it looks almost exactly the same. We're still shading in between, but what changes is we changed A from a less than to a less than or equal to, which means it changes from parenthesis to a bracket. But B is still a less than symbol, so that's still going to have a parenthesis. And then in interval notation, when I'm reading it left to right, A has a bracket, B has a parenthesis. So what changed here was just that one inequality symbol changed only slightly in the set builder. The graph had slightly changed, and then the only change was that one endpoint associated with that symbol. And so we've got basically two more combinations of this. I can have both of them be a less than or equal to symbol, or I can, let's see, make only B have the less than or equal to symbol. So those are the two other possibilities that we can do here. So set builder notation, you kind of get used to writing it because it's basically the same thing over and over again. Oops. So on the graph, and you don't have to label infinity and negative infinity, but I find it easier for graphing purposes to remember that one of these is infinity when you do that. So if they're both less than or equal to, or x is still in between these, but now they're both brackets. And so what that changes with interval notation is that you have these two numbers, and now there are brackets surrounding them. And then we have our last one here with A and B. And let's see, so we're still in between these. And we have a less than symbol at A, so that's a parenthesis. And then at B is a bracket because it's an equal to. So parenthesis A, B, and then bracket. So those are all compound inequalities where you're going to have answers in between two things. And that usually happens when we start taking intersections of sets. And then before I start getting into those intersections, let's just talk about if we have no solution, if we're solving, or if we have a solution, basic infinite solutions, it's all real numbers. So those are special case solutions. So no solution, you can use the no solution symbol, or you can use the empty set, empty like that. And if you're asked to graph this, it's literally a blank graph. I've seen this come up in ALEKS where it's no solution. And it's just literally a blank graph, and you just leave it blank because there's no solution. And we don't really have an interval notation, so usually we'll just use the empty set symbol instead of rather using the set builder notation or with the curly braces. Now, all real numbers, and there is actually I think it might be a quiz question or a homework question on this. So if you want to write it as a set, you can write it with x and then that vertical bar, then x is a real number basically. I think ALEKS wants you to actually write is a real number, which is a lot to write. That's why I use the shortcuts and the symbols because it doesn't take so much to write. But that's another way to do it, is to actually literally write x is a real number. When your solution, when you're graphing your solution here, your graph would be the entire number line. So you wouldn't be using any parentheses or really any brackets in between there on your graph, because it's just the whole number line. And then when you write your answer in interval notation, that's written from negative infinity to positive infinity, and infinity always has parentheses. So these are all the different ways that we can write these inequalities. And when you solve equations with inequalities, zoom out, there's a lot of them, you would be writing your answer in one of these notations depending on what the question asks. If it says to write it as a set, you'd be using set builder notation. If it asks for interval notation, then that's what you would use. You'd use the parentheses and the brackets. So let's talk about unions and intersections. So a union is basically all possible solutions. You can have overlap and not overlap. So union is that U symbol, which kind of stands for union. If we think about it as a Venn diagram where you have two different sets, so let's say set A is the one on the left, set B is the one on the right. The union would include answers that are in A, or answers that are in B, or answers that are in both. So it's basically every possible solution. So it'd be like your entire Venn diagram there. That would be the union. So the opposite of the union is the intersection, which that symbol is the upside down U. And actually, in math terms, this is called big cup. And then for whatever reason, this is big cap is the name for the symbol. I don't know why it's called cap, but it's basically an upside down U. And so that is only the overlap. And so if you are looking at a Venn diagram of two different sets, A and B, that's only where they overlap or intersect each other. And so when you're looking for the union, or you're looking for everything, when you're looking at the intersection, you're looking for just the overlaps. So I don't think I'm going to be able to get to everything about these. I don't think I can get to like actually solving these, but I can definitely, or at least solving the equations, but I can definitely do examples of intersection and union because a lot of people struggle with that. So let's say we have two sets. Given set A is, let's say it's going to be x less than 2, where x is a real number. And then set B, x is greater than -1, where x is a real number. So those are our two different sets. And when we want to, let's say, find the union, so A union B, and then A intersection B. So we'll find both of these. And I do these with number lines. So I'm going to put 0. I've got 2 and -1. I don't really care about the scale on my number line, but I'm going to make number lines. And then what I do is, so for the union, actually I do this for both. I basically write my two sets above it so that I can visualize what I'm doing, and then I put my answer on the line itself. So for x less than 2 here, so we want to go back to our kind of chart here, our less than, we're going to use this graph with the parenthesis. So At 2, I'm having parenthesis, and then less than is going to be everywhere left. So I'm just kind of putting that in the air for set A. We're just kind of visualizing or indicating what that means. Set B is x greater than -1. So at -1, it's a greater than, so it's a parenthesis, and then greater than. So I'm going to the right. So you can kind of visualize that way. You can see where they would be overlapping and where you would be having the union. So for the union, your answer is anything that's basically covered. So I'm shading here from 2, and I'm shading here from -1. And if you're looking at my picture, I have the entire number line shaded. So the union would end up being the entire number line are all real numbers. So A union B would be some value x where x is a real number, if you want to use the set notation, or you can just write it as an interval notation, -infinity to +infinity. Because when I basically drew wherever I had solutions, my entire number line was covered up. Now the intersection, so I'm going to draw the same number line and try to line everything up. So the intersection is where are they overlapping? And so we're overlapping. At first I want to see where the line is overlapping. So our 2 lines are overlapping between -1 and 2. And then you need to determine your endpoints. So if you have a parenthesis at an endpoint, that always trumps the brackets when you're doing an intersection. So that means I'm going to use parentheses here. And in this case, both sides were parentheses. So it kind of makes sense. Okay, my endpoints are going to be parentheses. And we use parentheses because one, like if I look on the right endpoint, set A does not include 2, but set B does. So they don't actually overlap at 2 because 2 is not included in both. So my overlap is between -1 and 2. So it may be helpful to then look for the graph that looks similar to that, so that way you know how to write your solution, either in set builder notation or in interval notation. So a union B would be, we are between -1 and 2. X is always in the middle, and then because they are parentheses, these are less than symbols. So -1 is less than x, which is less than 2. And then x is a real number. Or an interval notation, which I prefer because it's actually shorter to write. We have parentheses, -1, comma 2. So let's do another example. Let's say we have set A, where x is less than or equal to 5. And then set B, where x is greater than 7. And let's say we want to find the union and the intersection. So again, I'm going to make a number line and I'm going to graph these out so that I can visualize these things. So I've got 5 and I've got 7. So I'm less than or equal to 5. So at 5, I'm going to the left, and it's an equal to, so that's a bracket. And then I've got greater than 7. So greater than is a parenthesis, and we're greater, so we're going to the right. So if I want to find the union here, I have actually a gap. If I were to basically draw these on the same number line, there is a gap because we don't have two things connected. So A union B, we have to write these two things separate, and usually we'll use interval notation for this just because it's a little bit easier. So the interval notation for A is -infinity to 5 with a bracket, and then union, and then we have a parenthesis at 7 to infinity. And we use the union symbol to indicate that we have two separate pieces, but they're both part of the answer. So we're combining them together in the answer. So we have to use that union symbol there. Now, if you were looking for the intersection is the overlap. And if you're looking at my graphs here, there's no overlap between either of these two sections. And you can see that even on the union picture that I drew, that there's no overlap. So the intersection would be no solution, or basically the empty set, because there is no overlap. So it's important to know the difference between the union symbol and the intersection symbol, because that indicates, it makes a very big difference on your answers here. Then I'm going to do one more. There's not a lot of time here. Let's say A is equal to -2 less than x less than or equal to 3. And then B is equal to x less than or equal to let's actually do x is greater than or equal to -2. And again, we want to find the union and the intersection, just to practice these. So I'm going to draw my number line. And I've got -2 and 3 on my number line. So A, we have a compound inequality, so we're between these two numbers. So I'm between 2 and 3. At -2, we're using the less than symbol, which is a parenthesis. And at 3, we have the less than or equal to, which is a bracket. So that's what I look like there for A. For B, we're greater than or equal to 2. So the equal to means we're going to have a bracket. And then we're greater than, so we're going all the way across. So if we're looking at the union, we're looking at, okay, where are our lines shading? So that's A. And then we've got B on top of it for a section. And then we need to figure out our endpoint. So on the left endpoint at -2, we have a parenthesis and a bracket. For unions, I should say this, the union, the bracket trumps the parenthesis. So we're going to use a bracket, because Union means whatever you can include, and if -2 is included on one of the answers, then it's included in the union. So A union B, based off our drawing, is basically all numbers greater than or equal to -2. So x is greater than or equal to -2, which is the same thing as B, essentially. And an interval notation, that would be -2 with a bracket to infinity with a parenthesis. Now for the intersection, it's the other way around. Parenthesis trumps brackets. So it's important to know, because if it's not included in both, it's not included in the intersection. So if I was to draw my number line to graph the intersection, they overlap roughly, basically between -2 and 3. You can see that's where the two of them are both graphed. Now at -2, the parenthesis trumps it. And then at 3, one has a bracket and then one just keeps going. If it keeps going, that's sort of equivalent to a bracket, and so then we use the bracket symbol there, because 3 is included in both of these graphs. So our intersection is numbers between -2 and 3. So -2 is less than x, which is less than or equal to 3 because of the bracket, which in interval notation would be a -2 with a parenthesis to 3 to a bracket. And that actually is the same as set A in this case. So I know this was a lot of information on sets, and we lost pretty much everybody else while I was going through this. Does this help? Did this clarify for you?
Yes, that helped out a ton.
Okay.
It did.
Good. It's like, I know this is going to be a lot, but I didn't want to. But I think for everybody else, they were probably like, this is too long, I have to go.
Yeah. I wish I would have held off on that quiz now that I've seen all this. It definitely, it makes a lot more sense to me now.
What I recommend doing is taking a quiz Tuesday.
Yeah,
don't try to do quizzes early.
Yes, I'll learn that tonight. Actually, I took that quiz right before this this little tutor right here. So yeah, wish I would have done that, because everything else I was pretty good on except this, and